Hello, my name is Natalia Gervits. I am researcher in Lebedev Physical Institute, and today I will tell you about ferroelectricity. The history of ferroelectricity started in 1920 when Joseph Velasek, a PhD in University of Minnesota, reported about strange properties of Rochelle salt. Here is the formula. He observed two critical temperatures. He observed spontaneous polarization and piezoelectric effect. I will refresh you about piezoelectric effect further. In 1933, Kurchatov proposed an explanation of the ferroelectricity in Rochelle salt, and this explanation involved the dipole-dipole interaction of water molecules in this Rochelle salt. From 1935 to 1938, the new class of ferroelectrics was discovered. In 1941, Slater explained the ferroelectricity in this new group of materials, and his explanation involved the hydrogen bonds and two different dipole equilibrium states, orientations. And he said that the presence of hydrogen bonds is inevitable for the occurrence of ferroelectricity. The ferroelectricity in the new group of materials, such as barium titanate, was also expanded Slater's theory, and the explanation involved the displacement type transition. What are ferroelectric materials? Ferroelectric materials are the materials for which two mandatory conditions are fulfilled. The first mandatory condition is the presence of spontaneous polarization without external electric field. And the second condition is the responsiveness of this spontaneous polarization to an applied external magnetic field. And there is one more property which tells us that the material can be ferroelectric, is a high value of electric susceptibility under some conditions, usually temperature. So, what are ferroelectrics? Ferroelectrics are dielectric materials possessing spontaneous electric polarization, which can be switched or tuned by external electric field. Usually, we divide ferroelectrics to two classes. The first class is order-disorder ferroelectrics. These are the materials consisting of polarized polar molecules, which are able to spontaneously align to form a net polarization. The second type of ferroelectrics is a displacive type ferroelectrics. It's a group of ferroelectrics which in paraelectric non-polar state are symmetrical, but at some critical temperature, because of distortion, they gain dipolar moment. I'm pretty sure that you already know what a dipole moment is, but let me refresh your memory. Often in physics, we ignore the size and the dimensions of the object, but sometimes, for example, when we have two point-like charges, one is positive and the other is negative, you see the blue one and the red one here, and they are placed at the distance of d, one from another, we are talking about a dipole with a dipolar moment. Magnitude is a product of the charge and the distance. And this dipolar moment is directed from the negative charge to the positive one. These dipoles are neutral by sum of charges. They are responsive to electric field, and when this dipole is in the electric field, he tends to rotate along the electric field. Let's look at some examples. For example, carbon dioxide picture in the center. We know that all the ions have charges. The oxygen is negative, oxygen ion, and the carbon ion is positive. But what do we see here? We see that the shape of the molecule is symmetrical. And if we use the formula for an ensemble of charges, it's presented on the left, we see that the angle of this molecule, it's P, its symmetrical shape, leads to the nullified dipole moment. At the same time, if we look at the water, we know that the water is not lined up. there is an angle between the oxygen to hydrogen bonds. And this angle gives us the projection to the vertical axis, and this projection provides us, if we count everything, sum up, provide us a non-zero dipole moment. So we can say that a molecule of water is polarized. So before we talk about the first mandatory condition, the spontaneous polarization, let's talk about polarization itself. What is a polarization? The polarization of material makes the material responsive to external electric field. There are different sources of polarization. For example, when we have electronic polarization, there is just imagine some nuclei with electrons around it. The negatively charged electrons are pushed from the positively charged nuclei. So under the external conditions, the dipole is created. That's electronic polarization. About ionic polarization, under some conditions, one of the types of ions, or sometimes types of ions in the symmetrical structure, are slightly displaced. And this displacement leads to rising of a dipole in the previously symmetrical structure. This is the main mechanism of the displacive type ferroelectrics. The third type of polarization is dipolar polarization. In some cases, we already have elements which are carrying dipole moment. And under external field, or in some other conditions, these molecules just tend to align and to give the material the net dipole moment. This is the mechanism for order to disorder type ferroelectricity. All these type of polarization occur under the influence of external electric field, but, surprise, in some materials, at some temperatures, at some pressure, this polarization can occur and without any external electric field. Then this polarization is called spontaneous polarization. And a little formula. When we talk about electric polarization, we should know that to the electric displacement field, it's here up in the formula, we just have one more term, P, for polarization. And sometimes, for example, in ferroelectrics, this second term P is so huge that the first term can be neglected. For example, we see here that the permittivity for the ferroelectric material consists of susceptibility plus 1. You can see it here. But when the susceptibility is thousands, this 1 can be neglected. So if you see that instead of D in some formulas is used P for ferroelectrics, it's okay. Now a little theory. This this is a simple model based on Landau-Ginzburg theory. It stands for a uni-axis ferroelectric. The polarization here is chosen as an order parameter. And here on the top you see the free energy for this simple ferroelectric. You need to know that all the coefficients B, C are dependent on the temperature. And F0 is free energy of this ferroelectric in paraelectric state without polarization. What do we know? We know that each system wants to be in its minimal energy condition. So let's analyze this equation and find the minima. I hope that you remember how we do it. So we get these two equations, and we get two cases. One case when the temperature is higher than critical temperature, we will call it temperature Curie. It stands for zero spontaneous polarization and positive B coefficient. It depicts the paraelectric phase. So this paraelectric phase, the susceptibility, can be described by Curie-Weiss law. It's in the left bottom corner. You need to remember that you can use Curie-Weiss law only for paraelectric phase. And the second solution is for the lower temperatures lower than critical temperature, and there are two solutions with negative B coefficient. This second set of solutions gives us the double well symmetrical structure, as you see on the left. There is minus P spontaneous plus P spontaneous. So, as you remember, we are talking about uni-axis ferroelectric. So, the spontaneous polarization can have two directions. One we name positive and the other we name negative. And the spontaneous polarization in both directions is equal. So, to minimize the energy, material will choose one of these direction of spontaneous polarization. And in this case, when the field is switched off, the all two these positions are equal. What happens if we switch the field? Then, as you remember from the previous slide, we switch on the new term, product E electric field and polarization. And what does it do? It alters the landscape, the energy landscape, so that one of the directions of polarization becomes more preferable, and the bigger field is, the more preferable is this direction. Let's come back to Curie-Weiss law and Curie-Weiss temperature. Curie-Weiss temperature is a constant which is different, intrinsic for each material. And Curie-Weiss law at the nearest neighborhood of the temperature of Curie-Weiss, critical temperature, doesn't work well. You can use it, but you need to know that the calculated value will be overestimated. Sometimes in some materials, such as barium titanate, we have several critical temperatures. We see it on the right graph. So we have several Curie-Weiss laws with different constants, and on the dependency of the susceptibility on temperature, we see several peaks. By the way, do you remember that I told you that the coefficients in the free energy depend on the temperature? Here you can see the energy landscapes for barium titanate at different temperatures, at two critical temperatures and between them. Let's have a look at a displacive type ferroelectric. It is barium titanate. It has a structure of perovskite, and in nonpolar phase, it is a cubic perovskite. The barium ions are in the corners of the cube. The titan is in the octahedra of oxygen. This structure on the left is centrosymmetric. And length of the bonds between the ions is twice as big as the sum of oxygen and titan ionic radii. So the titan atom feels pretty loose in this cell. When the temperature is higher than Curie point, the thermal movement of ions keeps them centrosymmetric, the whole cell centrosymmetric. But when the temperature is lower than Curie point, the titan atom becomes localized near one of the oxygen atoms. And now the structure stops being centrosymmetric. So the symmetry is corrupted, and now the cell has a dipolar moment. Moreover, the localization of titan near one of the oxygen also leads to the structure transition, and the structure from cubic becomes tetragonal. The interaction between charges in neighboring cells makes them choose the positions, the oxygen atoms, consistently. So there are formed domains of cells with a titan atom choosing one particular oxygen. So there are 6 as the number of the oxygen atoms variants of titan atom displacement, and there are 6 possible variations of polarization direction. For order disorder ferroelectrics, there are polar elements, groups, which have several equilibrium positions, and at temperature lower than Curie temperature, they just choose one or several equilibrium positions and also form domains. So here we are talking about the domain structure. In the left bottom corner, you see the domain structure of barium titanate. You see that there are neighboring domains with arrows. Arrows stand for polarization direction, and the arrows in these neighboring domains are directed in different direction. The linear sizes of these domains, and all the domains in most of the materials, are from nanometer to micron size range. Now look at this picture. Here on the left, we see domains of ferroelectric without any external field and without history of applied external field. What we see here, we see that the directions are over the domains are different, and the net polarization of this material is 0. What happens when we apply external field? Under external field, we see that the domains are changing. There are 3 ways of changing the domains. The first one, the walls of the domains are moving. The walls are the boundary between the domains. They can move so that some of the domains become bigger. Those are the domains with the more preferable direction along the external electric field, and at the same time, some of the domains, the ones which the direction of polarization in which are forming the sharp angle with the direction of external field, are rotating. Their net polarization rotates so that it lies along the external field direction. And the third mechanism is occurrence of new domains inside initial ones. So if you have one big domain and the direction is not good enough, there can just occur a small grain of the domain with a preferable direction, and this grain will grow, and then the initial domain will just become the domain with the direction along the external field. Of course, rotating and other mechanism of domain changing needs time. It doesn't happen just in a click. So the polarization is just a little delayed in comparison to the electric field. This process takes place, and at the end of this process, if the electric field increases and is big enough, the whole ferroelectric material becomes one domain with the polarization parallel to the direction of external field. This response of the spontaneous polarization to applied external field forms a hysteresis loop, a special type of graph. We'll see it on the next page. If you have already learned about ferromagnetics, yeah, it's okay, because ferroelectrics are named after ferromagnetics. Here you can see the hysteresis loop. In case you have never seen it or never worked with ferromagnetics, I will describe it. Let's look at the center. At first, we have a ferroelectric never exposed to external electric field, and it has no spontaneous polarization. We are in 0, 0. Now look at the dashed line. We apply electric field and it increases. What's happening? The domains are reformatting so that they will align along the direction of the electric field. The spontaneous polarization grows. It somehow grows, and then when all the domains reformed to one domain system, we have saturation. Of course, the polarization will grow further, but it will be linear growth, and it will be produced by other types of polarization, not ferroelectric polarization. So that is the saturation polarization, and that is the saturation electric field. Now, what do? We decrease the electric field. And when we decrease the electric field, the domains, they remember everything. They somehow change, but when the electric field becomes 0, we still have polarization. That is called spontaneous polarization. So we have material in 0 field which has spontaneous polarization. What do we need to make the spontaneous polarization 0, to eliminate it? We need to apply more field in the opposite direction. We apply more field in the opposite direction. At some field, we call it coercive, or we call it coercivity, or sometimes it's called coercive force or coercive field. It's okay, or now all the variants are okay. We need to apply some coercive field in the opposite direction to make the spontaneous polarization 0. Now, if we continue increasing the electric field in the opposite direction, what do we see here? We see that the same ferroelectric, is polarized, is saturated, but in a different direction. So we have saturation here and we have saturation here. One direction it can be plus, other direction it can be minus. When we will work with memories, this can be 1 and this can be 0. So what do we do here? Now we decrease the electric field and get spontaneous polarization, reversed spontaneous polarization. In general case, the modulus of these polarizations in both directions is equal, and coercive fields are equal. Now we need to apply coercive field or coercive force to drive out the polarization from this material. The loop we depicted here is called hysteresis loop, and it's the same as we observe in ferromagnetics. So while switching electric field, we go from plus electric field to minus opposite direction. The polarization of materials in these coordinates gives us a hysteresis loop. It is the intrinsic property of ferroelectrics. And again, the polarization consists of both of spontaneous polarization and of the electric field induced polarization. There are other types of dielectrics. For example, linear dielectric on the left side there. There's linear dependence. Paraelectric, that is non-linear dependence. And ferroelectric, the only one that has a hysteresis loop. If we exclude the induced polarization, the hysteresis loop would have a horizontal upper limit and lower limit, of course. In both cases, in linear dielectric and paraelectric, when we switch off the external electric field, the polarization returns to 0. But in case of ferroelectric, switching off the external field leads to spontaneous polarization. In magnetism, when we are talking about ferromagnets, there is no spontaneous magnetization. It's called remnant magnetization, just for you to know. Now let's look at other properties of ferroelectrics. Since ferroelectrics are part of piezoelectrics, they also have piezoelectric property. They demonstrate piezoelectric effect. What is a piezoelectric effect? It's ability of certain materials, non-polar, to produce electricity upon applied mechanical strength. So what do we have here? That here is the molecule of quartz. Quartz is non-polar, but under compression or tension, the molecule becomes polar, and we have and now we have polar molecule. And there is converse piezoelectric effect. If we take some piezoelectric, for example, quartz, and apply an electric field to it, it becomes deformed. Since ferroelectrics also belong to class of pyroelectrics, they demonstrate the pyroelectricity. What is pyroelectricity? Is the temperature dependence of the polarization. There is the effect that when we from pyroelectric phase go to ferroelectric phase, at some point, at Curie point, as we already know, the polarization occurs. But when we lower the temperature, it doesn't stay constant. At the temperature decrease, it increases. It depends on the type of transition. For first order transition, we have a more abrupt curve, and for second order transition, the curve is more steep. The pyroelectric coefficient describes how much the temperature changing influences on the electric displacement field. But when we use this formula, we have generalized pyroelectric coefficient, which consists of the influence of temperature on induced polarization and spontaneous polarization. And if we need to know about true pyroelectric coefficient, we just take the first term. The last but not the least property of dielectrics for today is dielectric response. We already know about dielectric susceptibility, and we have seen that it shows us a sharp peak near the Curie point. So, how can we describe it? When the ferroelectric is in non-polar phase, but near Curie point, the right slope, the high temperature slope of this peak, a small field can induce a large polarization. And when we move to the polarized polar phase at the temperature beneath the Curie point, the effect decreases. What do we have to know about the dielectric losses which are produced by intrinsic properties of ferroelectrics? What are losses? It's an addition to permittivity, left upper corner. It's an addition to permittivity, and losses are usually described as tangent of tangent delta. This tangent delta is inversely proportional to Q quality factor. What do we need to know? We need to know that these dielectric losses, this tangent, is proportional to the energy we spend to change the polarization from minus spontaneous polarization to plus spontaneous polarization, divided by product of polarization saturation and electric field saturation. And the job is depicted by the area of hysteresis loop. The bigger is the area of the hysteresis loop, the bigger are the losses. Where can we use ferroelectrics? Including their piezoelectric and pyroelectric properties. We can use them in sonic and sonar devices, laser modulators, dielectric amplifiers, frequency stabilizer, temperature control elements, etc. And of course, we can use them in the memory. Let's look at the cell of FRAM, FRAM, etc. Ferroelectric random access memory. At first, ferroelectrics were proposed as material for memory storage in 1955 by Dudley Allenbach. In 1994, it was first used in industry by Sega in chips to store saved games, and now FRAM projects are on in all the leading R&D companies. What are the pluses and minuses of these FRAM cells? Let's discuss the mechanism of their work, and then we will discuss the pluses and pros and cons. If you know how DRAM memory cell works, it's almost the same. You see here that the elements are stored in a bit line. Here it is. And there is a word line across these bit lines. The crossing of the bit line and the word line is the address of the cell. The ferroelectric material is a capacitor. And what do we have here? Do you remember the hysteresis loop? Of course you do remember. The polarization, the direction of polarization of the hysteresis loop is 1 bit. For example, when the direction is up, it's 1. When the direction is down, it's 0. How will we write this memory bit? We apply field to this capacitor and change the spontaneous polarization to the desired direction. Now we turn off the field, and the polarization, since it's spontaneous polarization, remains. Now you can take this system, just switch all electric devices and put it somewhere on the shelf. And when you need it, you can take it and read it. So it's a non-volatile memory system. It requires power for reading and writing, but it doesn't require power for storage. And how do we read from this cell? It's a bit different, and it's not that convenient. We do not read, we write on this cell. We write, for example, 1 in this cell, and if this cell is already 1, then there is no response from the system. But if the cell is 0, so the polarization is negative to the polarization we want to have, or we don't want to have. We want to know what is the initial polarization. So we apply the field which will provide us some polarization. And if the applied field changes the polarization, we have the response of the system. And the presence of this response gives us the information about the state the system was before we interacted with it. So, on one hand, now we know about what was in this cell, but on the other hand, we just destroyed it. So, to storage the memory, it needs to be rewritten. So, this process, the process of reading, is more complicated, but it's okay. We know how to write. So we have read it, and now we write back the information we just read. This is one of the cons. The reading of the memory cell is a destructive process, and you need time to write it back. The other problems are low density and very, very high price. But there are more pluses. The main plus, in comparison to other random access memories, is the immunity to strong magnetic fields. Since the system is about electricity, about polarization, it doesn't feel the applied magnetic field. That's all for today. Thank you for your attention.